Hey everybody, it's my birthday today. I turned 25. And last night I was playing Kirby's Dream Course with Electro Noob, my good friend. And we were playing on NetPlay. And in the middle of playing, Electro Noob said, "Wouldn't it be cool if all the enemies could turn into UFOs? Why don't we do that? Why don't we hack the game?" And then Electro Noob was all like, can't be asked to hack the game. But I really wanted to do it. I wanted to try it out. So um, I went in after I, closed out of Electro Noob, and I hacked the game last night, and I want to show you guys the what happens in the game, and then I want to actually go through the entire hack and how I discovered everything that it took to actually get the hack to work. And this means I'm going to go through like the tools I use and how I use them. In full. So first off, let's do the hack. Like let's actually watch the result of the hack. Oh great, I get to go first. Alright, so I'm just gonna go for any of these guys with power-ups. I'm gonna do an aerial shot. And I got UFO now. And I got another UFO. Nice, I almost sunk it. So that's the UFO hack. That is the UFO hack. Now I want to talk about how it was done. And I really mean this in full. So how was this done? I have like a little folder here called Kirby Hack with some notes to remind myself. Plenty of images that I took going through it. Here's one just for fun. So you wouldn't believe it, but Electro Noob actually managed to land himself here, right in front of that Gordo. Wow, Electro Noob rules. So that was actually that was when we were playing. That was last night. But where's Sublime? Is this thing working? All right, so get to level Gordo. The first thing was get to a level where a two player level, and one where there was like a power up easily accessible. Yeah, let me look at the notes one more time, make sure. Snapshot. Yeah. All right, we'll get to step 2 after we load it up. So I use my own kind of customized version of BSNES, which I've got like strictly an Xcode, Mac OS X project for. So we're gonna load this up, and I got this updated. I hacked it to work it on Mavericks, which deprecated the Carbon API, which this is an older version of BSNES, which has a debugger in it. It runs slower though because it's older, but I don't think the newer version has a debugger. Correct me if I'm wrong. So now I'm going to load this ROM up. If I can find it. There it is. Where's BSNES? So the first thing is, like I was saying, to get to the part in the game, I have the audio turned off in this case. It's really slow, so it sounds really bad. Gordo has an easy, accessible power-up enemy that we can hit and we can play with. So I actually have save states where I'm going to get into how we use save states. So at this point, not only because the emulator is slow, but just because it's advantageous to do so, I go into the Tools State Manager, and I'll save a save state here so I can when I load up the ROM again later, I can immediately arrive in this state. As you see, I've already added a bunch of them, and I'm gonna save a new one right now. Oh crap, I just loaded it. Alright, well let's see. About to shoot. See that? So that's an older save state that puts me in the same exact spot. So this is really useful, and that's one of the first things I'll do. Next is you know, the SNES has tons of RAM. Well, I mean, to a human that wants to disassemble and reverse engineer it, it's tons. I guess in the compared to modern world, it's not tons. Hey.
Hey, boo boo.
So I'm doing the video now, and I totally didn't have you do the intro.
That's okay. Want me to do it now?
I probably not, because I'm kind of like,
I'm kidding.
yeah. So I'm just gonna like finish up this video and
That's
then
fine.
cool. All right. So the whole idea is, in my mind, I assume that it must be a RAM location that the current player's power up, whether he's player 1 or player 2, gets stored. So what I first did, I mean, if you really want to, I'll give you like the very full story. Is I went to the debugger, which is here, and then I went to the, where did I go? To the memory, and I was playing around with the RAM, which we can find in bank 0 from 0000 to 1FFF, but we can get the full RAM in bank 7E, so I was really at 7E. At first I was just screwing around, changing values in there. Then I realized this could go on all day, you know, and I have really no hints when I'm just at a big smudge of RAM. So what I decided to do was what I wrote in step 2, which is to get a snapshot of the RAM before and after I get the power up. So what I would do is I would take the shot, so I'll take the shot right now. Make sure you have the debugger window open. I would take my shot, get ready to brake, and I would brake like right now. So I'm like right before I hit the power up. The closer you get without hitting it, the better, because the smaller your thing's going to be, your snapshot. So at this point, what I would do is I would export the memory. And then when I export it, what happens is it goes into a folder with the same it's in the same folder as your ROM. In my case, unless you have different settings, I'll talk about that too. So if you go into your BSNES preferences, in the paths, you know, there's exported data path, same as loaded game for me. And it'll go in a folder of the same name as the ROM. And I've renamed them because I had to take 2 images. And you'll get all of these binary files. The only one that I wanted was the work RAM. So once I took these pictures, for instance, I would have exported it right now. Click that, and then I would have gotten ready to run it and break it again like this. Oh, see, that was kind of bad. I went for a while there, but I would have saved a state. Obviously, see, that's what I didn't talk about. I would have saved a state right before I hit him so that I could go back. But in this case, since I didn't do that, let's pretend this is a real situation right now. I would go back to my save states. I would redo my shot. I would have to go back here and say run, and I would just try it again. So at this point, I would break, I would do a save state, which I'll do just for fun. Hit save, about to hit power up enemy, you know, and then I'd save that. And then I can go and run and then break again, so, you know, something like there, close enough, and then I would re-export the memory. And now I have these 2 memory regions that I can do a hex diff on. And if you aren't familiar with that tool, if you're using Mac ports, you can just port install hex diff, I think. But it's like the diff command, which if you don't know about, you should Google that. But it works on like binary files, and you can view the differences in hex, so it's really useful. So what I would do at this point is I actually took a snapshot of this. I think what hexdiff looks like. This is what hexdiff looks like, but I'm also going to run it for you so we can talk about some useful commands that I used while I was using this tool. Something that's kind of odd is that you have to specify the file that came after as the first parameter instead of the file that came after as the second parameter. meaning that once I open this folder up, I'll show you what I mean. So I would do hex diff kdc after, and then what is it called? Kdc wram. So yeah, you got to specify the changed file first if you want the changes to look right. That was in my case anyway. That way, the changes that are highlighted are actually the new changes. Isn't that strange? That I don't know. I feel like the other diff was different. You specify the change file after, like regular diff, but. So at this point, I can see what has changed between before the power up was hit and after, meaning that I don't have to just pointlessly change values in RAM that will never do anything because they were never changed. So that kind of gets to make me a little more efficient in my search for the correct RAM location. So the very important key shortcuts in this tool that I use are the capital H to turn these offsets from decimal into hexadecimal. That way I can align these offsets perfectly when I'm in my SNES debugger, when I'm in the memory view, which is in hex. Of course, the bank 7E, it doesn't really show up in the diff because this is automatically 7E. Okay. So at this point, the next good shortcut is the letter N, and that'll give you to the next diff. So if I hit this, you see how it just goes to the next line of diffs, and I can use that to just go through the whole file. And I'll tell you, it was a pain in the ass. So when you look at sections like this, the weird thing about Kirby is that a lot of the RAM sections, when I edited one value, it would make a lot of other values change in a lot of these RAM sections, and it was really confusing. And I started, like, there's a lot of values that have changed, so I started losing my temper sometimes. And I would start skipping sections that looked like those same weird sections that I ran into that would like change other parts of RAM, because I felt like that was a different type of thing if it was going to be updating other values. I felt like a power-up wouldn't be doing that. That was just my intuition. I didn't have any real evidence to support that, but I started skipping values based on that. I definitely got lucky because sometimes I just skipped values out of pure anger that this was taking so long. So I mean, I got lucky that I didn't skip the important RAM value that changed the power up. But since I had no other tips or clues, I mean, this is the best option I had. So yeah, look at that. So I would go through here, and I mean, just to give you an idea of how many values I had to go through, lo and behold, I finally found the correct value, which, let me make sure I didn't miss anything. The worst part, yeah, the worst part was definitely this part. It was searching for the correct RAM address. Where did I find it? I found some weird stuff, like this. If you turn this to a 1, will activate the menu. This is kind of off topic, but see this little menu here? If it isn't showing and you put that to 1, wherever that picture just went, you put this address to 168F4, then the menu will go on for a certain amount of seconds, and then it'll shut off automatically. Just throwing that out there. It's something I found along the way. Something else that was random is that I also found this map adjust. Let's actually do this right now just for fun. So if I restart this, or re-enable the emulator, and I go to this thing that I found by accident, 7338A0, 7338A0. So I could adjust, I believe, if I recall correctly. For all I know, this is only for player 1, but we're going to try it. I think it was this one. You can adjust like the map. No? Let me just mess around with them. Oh, there it is. Yeah, see that? Whoa, what did I do? I think I just crashed it. Oh yeah, I totally just crashed it. Let's see, this is why you want save states. Along the way, there was various RAM addresses that when I changed them would just crash the game. So with the save states, that's totally useful. You can just go back. See that? Like, that's so useful. So let me go back to about to shoot. So apparently it was this value, or one of these. Let me go to 88. Yeah, see that? See how it's kind of adjusting where the map was, or whatever you want to call it, your camera? And then I just totally crashed at that point. That's something that someone might want to play around with. I'm not interested in that. But some accidental stuff that I found. Then finally I got it. And I found it at 7ED850. Now if we've been going through hexdiff, we're only at the thousands. So you could now get an idea of how far I went just to get there. D850. It's actually D852. So check this out. I mean, how many times can I hit N until I get to that? So, you know, going through all these, we're at the 5,000s by now. But I'm going to go through it all. I'm speeding up. I'm just going to skip all of it. I don't want to... Oh, so we basically got there. So yeah, through all that, finally found a value that was changed. And when I changed it in the game, it worked. And you see I got this rock power up. And I'm up there. It's hard to see. I just kind of took a small image. But let's do it live. 7ED852. Let's go there. 7-8-D8. 7E. I keep seeing 8. 7ED852. So if I change this low byte, watch the power up window. See that? He just became rock power up. Now he became the umbrella. That's 2. And then at this point I was learning the values that correlated to what power up. And of course I'm interested in the U.F.O. So I'm going up in the values. Bum, ba, da, bum. Get to 9, still not it. A, what do I find? U.F.O. So there's the U.F.O. And then I was like, well, what's after A? And then we see we got this weird power up, which is actually I had read about on a website about some like hidden stuff in this game. And apparently when you use this power up, it crashes the game. But I never tried it, so let's try it right now. Oh wait, the power up didn't even... Power up went away, am I right? I mean, where did it go? Strange. Anyways, that didn't do anything. I'm going to try it again. And I think if you do any value above this value, it also crashes the game. Oh yeah, that you can't even use that power up. It goes away immediately. I don't know what anyone was talking about it crashing the game. It just doesn't even allow it to be used. It just resets or something. It must be some sort of logic that checks that the power-up's in the bounds of 0 through A or something like that, and just ignores it if it's anything else or greater, you know? Okay. So now that I found out that it was this RAM location, it got a little more complex because now, okay, I know this address is where the power-up can be specified, but now it's time to actually hack the game, so you need to know where in the game is the code that is writing to this address. So here's how I found that. I go to the breakpoint editor, which is in the part of the debugger, and I've made keyboard shortcuts in my custom version of this debugger, so I can just hit Apple B, and I get my breakpoint editor. And at this point, I want to break on a write to 7E-D852. Once again, I'm going to check my notes. I want to make sure I don't miss anything. Found it yet. Where's the RAM getting written from? So this is where we're at right now. So at this point, I would do a check, right? And here's where it gets really weird. I'm going to break. I want to put this back up. Here's where it gets really weird. So let's have this up. We got a lot of windows going on right now. Whatever. So I'm about to make a shot. Watch what happens. Look at this. We broke immediately without hitting an enemy. So in my mind, while that's cool and all, I mean, let's actually just run this thing several times and watch it break like every single frame. So just breaking and breaking, and this value is continually getting stored to. I mean, this address is continually getting written to. The only problem is, see, it was possible for me to just take a look. We have a disassembler, which I can open up. Disassembler. And this will show me what's the disassembly around the current PC address. And I can see that this load a D9C4. So now, like, I'm going, okay, what? At first, a lot of things was going through my mind. I was just processing what had just happened. And let's break it down. This thing is being stored from the value at another RAM location, D9C4. So the problem I had before I even talk about hacking this RAM or this address opcode was that it was happening every frame before an enemy was being collided with. And that means that if I did the hack at this point, the person would just have UFO at all times because he doesn't even have to hit an enemy. And I thought that was a little more lame than being able to hit any enemy and get a UFO. Because I mean, once you hit the enemy and you get the UFO, it's kind of all over. But if you just have it off the bat, I don't know, like. And that goes into the next hack that I would like to do, which is instead of all the UFOs, to make everyone what I call a cake, but I think is really called a transformer, which actually scrolls through all the power-ups, and then you randomly like hit A and you get an assigned power-up. It'd be cool if all the enemies looked like their regular selves, but they had that like thing that they do to give you the random power-up. Okay, so yeah, basically I had a problem with this RAM, with this. So how did I get around that? I'm just thinking back. I'm just going to take a look. Oh, I must have said to myself, okay, well, what is writing to this address? Because this RAM is the one that's writing to this RAM. So what's writing to this one? So then I set a new write point. A write breakpoint. And I set it to this D9C4. Of course, before I could really know that this was D9C4, I had to look at the data bank, which is 7E, and then I know, okay, I got my full 24-bit address. So 7E D9C4. Set a write breakpoint on that one. And I'm going to take this other breakpoint off. I don't remember exactly how I did this when I actually did the hack, but this is what we're going to do this time. So we're going to run it. And the whole idea, if I recall correctly, is that I want to see if this address gets written to at every frame like the other one, or if it will get written to only when I hit an enemy. Because that's like the whole thing I want. I want it when it hits an enemy. So we'll run it right now. And it looks like something just broke. Breakpoint 1 was hit as well. So now breakpoint 1's hit, and I can look at the disassembly again, and it gets even crazier. Now we're seeing load A from D852. So it's like they're like loading from each other and writing into each other. Is that confusing or what? I don't remember what I did. Let me do another breakpoint on both of these. Jeez, I don't remember what the heck I did. Oh, you know what I think I did? I think what I did was I ran this a million times, and even though it was, you know, breaking like 100 freaking times, what I did was, I don't recall if I had both of these on, but I'm going to leave them both on. It's going to be a little more difficult with them both on. So what I'll do is I'll turn one of them off just to advance the frames at twice the rate as they would have. And what I do is I'm going to go and keep going until Kirby gets really close to the power-up. So I'm just clicking on and off on the run and break. Of course, you could disable all the breakpoints and do this faster, but this is just the way I'm going to do it right now. Exercise these fingertips. So here was the whole idea I had at this point. I looked at it. At this point, you know, you might want to have another save state. I'm just gonna do it just in case, you know, demo breakpoint before hit enemy. Such a general like thing, but there it is. Okay. Now, what I was interested in was, will these addresses get written to from a different code position in code when the enemy gets hit? So now I want to re-enable the breakpoint, like both of them. And I want to know if any of these guys get written to. And so basically I'm looking at how this is primarily, there was two addresses. We got to look for breakpoint 1. It looks like what did I miss it? There it is, breakpoint 1. So we're looking at 82 EFD. These are the typical addresses that we want to ignore. And I'm going to put them into the breakpoint editor, but I'm not going to set them, but I just want a place where I can have them easily visible. You could also put this in a text editor. But I'm down here now. Where's my breakpoint editor? I need all this stuff visible if possible. And I'm really close to hitting my enemy, and now I'm going to start running again, and I'm going to look and see if the address here will change. There's one that we've already seen. That one's also familiar. Let's wait until we actually hit the enemy, because it'll just be the same until we actually hit him. It might help to highlight the last place we were at, see if that stays highlighted. No, it doesn't. Oh well. Oh, hey, you see that? See what I'm saying? New address. So this is something that's like totally new, totally awesome. You want to copy that. I'm just going to at least put it on the bottom here. And let's keep running the code and see what happens. 82A70. So these addresses are so close that if we look at the disassembly here, we see that this is part of the same routine. So we only need this first address. We don't need the rest. But you know what's really interesting, we're going to get into it, is how we don't see anything before it. And that became a huge problem for me to overcome. And I'm going to talk about how easy it is to overcome in all actuality. So we basically found it, but I'm going to keep going, see if we see anything else happen. So you see that we got the power up at this point. But we're back to our old address, 82F17D. So we know that the new power-up was assigned in the assembly routine that happened at this new address that we got. And that's how I figured out where in code is this new power-up being assigned when the enemy is collided with. Once I had this, when we were at that in the code, which is kind of gone now, sadly, we saw that we got to go back to that. So I'm going to, once again, the usefulness of the save state, I'm going to reload the save state. Got to hit run if you're already broken. When I say broken or broke, I mean like literally you're not running. Okay, good, we're running. So I'm going to get back to that part that we break on. I'm looking for 82. You know, I could just set this breakpoint. Oh my god. Yeah, I could just set the breakpoint at this point and hit run. Alright, so we hit the breakpoint, and now we see, this is where it gets complicated or really confusing, is that we see the accumulator gets stored, and the accumulator has the value 5, which, if we were paying attention, is the actual value for the twister power-up, 0 being normal. So the question became, oh god, I can't see anything before, and now it makes you as the hacker developer wondering, well, where did the value that went into the accumulator come from? Because that's ultimately what you need to hack. Now at first that looked really difficult to me, because when BSNES shows the ... dots here in the disassembly, I interpret that, this isn't kind of an assumption, but I'm pretty sure it's true, is that it means that there was a branch to this address, or a jump, you know, some sort of branch jump combination, one or the other. That could be long branch. We're not going to get in any form of branching, jumping, whatever, subroutines or not. That's what I think anyways. So at first I'm going, well, geez, how I wish BSNES, this is what I was thinking to myself, I wish BSNES had like this branch or call backtrace, right? So the first thing I thought of, I didn't even get as far yet, but I'll give you the hint, is that I was going to look at the stack and see if I could divulge a return address. But before we get to that, literally I was going to see if I could be lazy, and instead of actually finding where the load A happened, I wanted to see if I could just overwrite one of these guys with the value OA. So, you know, like basically the desired opcode would be a load A, 0A immediate value, and then to store that A into the RAM offset, or the RAM address where the power-up's located. So I wanted to see if I could put that opcode in over one of these. For instance, there's a store Z DC9A. Now, of course, I don't know what that store Z does, but what I was thinking in my mind was, I know that the value that's really important is the D852, because that was one we messed with in the beginning, and it was actually changing the power-up. I don't really know if D9C4 is as important. So, like, the first hack I did was I actually put a load A here, and then I just F'd the store Z, just don't even store anything. And that actually didn't work. But what's important to talk about is what I did to get from the idea of the assembly instruction that I wanted to put in there and get to the hex equivalent. For me, like I said, I wanted to put in a load A, I'll write it down, load A, 0A. And the reason why I decided to use the load A was because we're storing A, like the natural program wants to store A to these offsets, which are where the power-up RAMs are. So if I can put it into A beforehand, then I can hack it. Before we get to the precise location where I'm going to put this hack in, I want to talk about how we get from this to the hex. So what I use is a file called 65816info, which I'm pulling up right now. It's something I have on my local hard drive, but you can probably find it by the title on Google, 65816info.txt. And this is just something that I grew up learning from. So it's where I go. I'm sure there's other documents that have the opcodes in detail. But I'm going to do a search for load A. And then I'm going to go down to the bottom because I just know that's where the opcodes are. And then I'm looking, I want to load a const value. And the opcode for that is A9. And it says 2 bytes. The important thing is you want to look at this point in the disassembly, or the breakpoint, and you want to look at the status register, and you want to make sure that the accumulator is 8 or 16 bits. The lowercase m and x mean that they're both 16 bits. If they're uppercase, it means they're in 8-bit mode. So that means this accumulator is in 16-bit mode. So I take a look down here and I read this little note: add 1 byte if the accumulator is 16 bits. So that makes my opcode in total, well, you know, with the parameters of the opcode, 3 bytes long. The first one's going to be A9, and then it's going to be the low byte and the high byte of the immediate value that I want to load into it. So what that means is that my complete instruction will be A9 0A00. So now I know what I want to put in. I just need to find the place to overwrite to put this in at every single time, instead of, you know, the power-up that correlates to the enemy that was collided with. So once again, we come back to this place where we're not like allowed in the debugger to see where did we come from, because wherever we came from is where the accumulator was loaded. So that's where a really useful feature in the debugger, which is called trace SCPU opcodes, comes in. And just given the incorrect compilation of this program, instead of putting this trace log, it's gonna, first of all, it's gonna put a file called trace.log. It's supposed to put it in the exported data directory, but there's an issue there. So on my computer, it actually comes up in the like the root of my hard drive. Let me see if I can find it. Oh God, where did it go? Here's KDC twister.log, but there should be, oh, there it is, trace.log. I'm going to take these and move them because I'm just totally fearing losing them right now. And I'm going to put them into my like Kirby hack directory, and then we'll talk about them. I'm just going to move them here. Okay, so like I said, automatically goes into this file called trace.log. Now, from the experience that I gained using it last night, I have the feeling that even if you start it in the middle of the game, the trace, I think that what gets output is the entire execution of the game. But I'm not really sure. But regardless of that, it's not too crucial, and it's definitely something that you should know. And if this is only speculation at this point, but that might be important for you to figure out if you're doing stuff like this. But the key is that with the trace, you get to see the entire execution of the game up to like the point you finish tracing, and then you can be able to see if we do a search for like this ROM address in the actual trace, we can look at what happened before this ROM address was executed. And the whole idea in our case is we can find where the accumulator was loaded from, and then we can change that opcode to something more suitable for our hack. So that's exactly what I'm going to do. And literally, what I would have done is I would have loaded my save state before I'm about to hit the enemy. All right, just like I don't want to have anything going on here. I want to be completely in break mode if I can. So when I hit run, this is going to go like, check this out. See, like that. So what I want to do is I want to load the breakpoint. I want to be broke. I want to load the breakpoint. It's actually loaded right now, even though you don't see it. The moment I hit run, it's going to run. So then I checked trace SCPU opcodes. And this is actually going to put that trace log, that file, which I'll just do it anyway. I'm going to run it, hit the enemy. Notice it goes slower when it's tracing. I stop it, and you want to stop this like immediately after, because this file is going to be big as fuck. I mean, there's like millions of opcodes that are getting run, you know, so that's why it goes slow. And then you want to stop tracing, and then literally, I don't think the file it does get written. I was going to say it doesn't get written until after you exit the emulator, but that's not true at all. So now I'm opening up. Here's the trace.log, and look at it, it's already 35 megabytes big. That's just regular text. So this is going to take like literally several seconds just to load into your like word processor. So I'm waiting for it to load right now. Also, like, you're gonna want to use a good computer for this, because that file, good luck searching through this file for keywords if your computer's slow as fuck. So what was that address that we were concerned with? I already kind of forgot. This one right here. We want to do a search for this address because we want to see what happened beforehand, and we can do that in the trace. So now I'm just going to do a search. I find this address. Here it is right here. So now I can look what happened beforehand. My speculation was correct that a branch happened, and that's why SNES was being a little bitch. I don't know why it wouldn't just show it. It would have made things a lot easier. But hey, now I get more experience using the trace. So we're going to look a little higher up until we see a load A. This is the guy that we want to kill. So this is where the power-up gets loaded from. We can change this into a load A 0A, hex immediate value, and then we'll have our hack. I mean, that's it at this point. So now the question becomes, okay, well, we're going to edit this ROM in a hex editor, but how can we easily find this address in the ROM address? Because, the ROM address differs from the SNES address. So here's how I did it. I think this is the easiest way in the context of the tools that I use. What I would do is I would take this address, copy it, and then what I would do is I would go into SNES, go into the memory, and then type that address in, then take this entire row of values, copy them, and then I'm going to go into the Kirby's ROM, which is where? Right here. Of course, I'm going to make a copy of it so I can have a backup of the original. I'm just going to put this on the desktop. No, we'll put it in Kirby Hack. Like, I'll call it demo hack. And now we open it up in a not text emulator. What the heck? A hex editor. Did that open? Demo. Yep. So I'm using 0xed. I just call it ed. This is on OS X, of course. And now what we do is we do Apple F, find, and I'm going to look for that string of characters. We want to make sure that we search in hex. And I think I can just type. Yeah, here we go. I'm using. Oh, this paste buffer is so useful. I can have like 80 things in my copy and paste buffer. If you don't have this and you're a developer, like get on this. I can literally copy and paste like zillions of different things and all have like this single copy and paste buffer, so I can work with all types of things, copying all multiple things at once. All right, so I put that in there. This whole entire search string. Since it's so long, it's going to be hard to have multiple instances of it. So when I hit find next, I want to make sure that I found the only instance of it in the entire file. So I do Apple G, and you see that it's the only instance of this. So I know that the BD1C53 is the opcode that's originally there, which is the load A531CX. And here's how we can make sure of that. We go back to 65816 info. We look at the absolute addressing X-indexed addressing mode, and yep, I'm making sure that it's 16-bit absolute address with the indexed X, and it is. And remember that we're in 16-bit mode, and we can check that again. We can look at our address, and we'll look at M, which is lowercase, so we're in 16-bit accumulator mode. So with all of that said, we're going to add 1 byte. Yep, that's great. Anyways, this is already a 3. You only add 1 byte if the star is there, which it isn't. So that's how you read this table properly. So we can actually ignore this right now. So we look for the opcode BD followed by what would be a 2-byte absolute address. And if we look in the hex editor, we see BD1C53. Remember that the address is low but and then high byte, meaning that the address is 531C. And we can verify that when we look at it in the trace, load A531C. So that is the entire opcode that we want to overwrite. And fortunately, the opcode that we're going to overwrite with is the same length, which is the 3 bytes. That introduces a really potentially complex issue if you were to have an opcode that was of different length than the one that you wanted to overwrite. So if anyone has any thoughts on that, on how to get around that, that'd be cool to listen to. So if you're the guy who knows about overwriting opcodes with different lengths than the originals, definitely talk to me or write a YouTube comment. All right, thanks. So anyways, in our case, we have a matching length. We already found the hexadecimal equivalent of the assembly instruction that we want to write. Here it is, A90A00. So I'm going to write that in right now. A90A00. I'm going to save this ROM. The ROM is saved. Now I'm going to just make sure that I wrote at the right address and stuff, so I can see my offset right here. But I mean, that's it, A90A00. Now that we've written it, we can test the ROM. So I'm just going to go ahead and run it in SNES 9X. I'm only using SNES 9X because I just have it. It's not like a thing. There's no reason why I'm not using BSNES. Aside from this being faster than that debugger BSNES, it's really slow. Even without the debugger, it's really slow. Alright, so I use the 2-player game because 1-player mode, you gotta create a save file and all that crap. Gordo is just the easiest one in my opinion, so. Oh, here's an interesting tidbit of information. I was going to suggest adding a save state to SNES 9X at this point, or actually prior when you had the original ROM, but my issue with that is I was wondering if a save state has like ROM save information, or would you just have, you know what I'm saying? I was kind of concerned if I saved state in the original form of the ROM and I restored it with the hacked version of the ROM, would the original ROM still be in the restored state? You see what I'm saying? I'm kind of doubtful that it would be, because ROM is read-only. Why would you put that in a save state? It doesn't make any sense. So, but those are my 2 cents on that. I think it's okay, but I haven't really tried it. I have problems saving and restoring states on this, so. But now that I've gotten through all that, I'm going to actually get Kirby to hit this power-up guy and watch him turn into a UFO. Yes, we got a UFO. Isn't that sick? Alright, I'm so happy about this. And every time you hit anybody, you get another UFO, so you can keep reusing it. Granted, you can't change the height that you're flying at, but it's cool. You can, like, nearly, on certain levels, you can, like, just annihilate everybody. Alright, so that's how I figured all that stuff out. I don't know how long this video is, but it felt pretty long. And I'm really proud of myself. So thanks for watching, and I'm totally clocking out. Alright, happy birthday to me! Peace out, I love you.